A child wakes inside a city with no horizon. Not a city under a sky, not a city on a planet, but a city sealed inside a machine. The air has already been breathed by the dead. The water in the cup has passed through pipes, roots, bodies, filters, membranes, and back again so many times that no one bothers to call it recycled anymore. Beyond the wall is not ocean, desert, or night. Beyond the wall is interstellar space, cold, almost empty, and so vast that the nearest star is still generations away. The child did not choose this journey. Their parents did not choose it either. Their grandparents may not have chosen it. Somewhere far behind them, people with open skies and gravity under their feet built the vessel, named it with hope, filled it with families, machines, seeds, archives, and promises, and pushed it toward a star none of the founders would ever see. The question is not whether this is inspiring. It is. The question is whether it is physically honest. The comfortable belief is that if the stars are too far for one lifetime, we can simply stretch the mission across many lifetimes, make the ship large enough, make the habitat closed enough, make the social plan wise enough. Let one generation carry the next, and let the descendants complete what the ancestors began. It sounds like patience turned into engineering. It sounds like the humane version of interstellar travel, slower than the heroic starship, but more plausible than warp drive. Yet the uncomfortable argument is that a generation ship does not mainly challenge propulsion. It challenges the idea that a sealed civilization can preserve machinery, ecology, health, knowledge, and consent across centuries, while the universe quietly taxes every ordered system aboard. A short interstellar crossing might be possible for probes. A carefully designed world ship to the nearest stars might not violate physics. But the longer the voyage becomes, the more the mission stops being a transportation problem and becomes a fight against time itself. The central difficulty is this: generation ships are not forbidden by any single law of physics, but most popular versions hide the real failure mode. They imagine distance as the obstacle and patience as the answer. In reality, patience has a cost. Every century in flight gives radiation more time to damage DNA and electronics, gives materials more time to fatigue, gives ecosystems more time to drift, gives institutions more time to forget, gives spare parts more time to become irreplaceable, and gives small errors more time to compound into fatal dependencies. The best counterargument is also real. A civilization far beyond us could build self-repairing factories, use artificial intelligence for maintenance, store embryos or gametes, shield habitats with water and fuel, rotate sections for gravity, and design ecological loops with more care than Biosphere 2 ever had. We should not pretend that today's engineering is the ceiling of all engineering. But even if those tools help, they do not erase the central physics. They buy time. They do not make time harmless. To see why, begin with the reason generation ships exist as an idea at all. They are born from a refusal to cheat the speed of light. Light moves through vacuum at 299,792,458 meters per second. That number is not merely the speed of a particular thing called light. It is the invariant speed of causality in special relativity, the speed at which massless fields propagate, the limit that massive objects can approach but never reach. A ship made of atoms cannot be accelerated to light speed because the energy required rises without bound as velocity approaches that limit. This is not a missing engine problem. It is a structure of space-time problem. The universe does not care how ambitious the mission plan is. The equation remains. The nearest stellar neighborhood already makes the point. The Alpha Centauri system lies a little more than 4 light-years away. Proxima Centauri, the closest known star to the Sun, is about 4.25 light-years away. The Alpha Centauri A and B pair are farther by a small amount. In ordinary distance, that is roughly 25 trillion miles. The number is almost meaningless because it is too large for human intuition. So compare it with what we have actually built. Voyager 1, launched in 1977, is the most distant human-made spacecraft, still operating an extended mission after entering interstellar space, but aging, power-limited, and managed through increasingly careful conservation. It has spent nearly half a century moving outward and still has not traveled even 1 light day from Earth. Parker Solar Probe has reached record speeds near the Sun, around 430,000 miles per hour at its closest solar passes, but that speed is achieved by falling deep into the Sun's gravity well, not by cruising across interstellar space. Even if you could aim such a velocity straight at Alpha Centauri and sustain it, the crossing would still last thousands of years. This is the first correction to the fantasy. The fastest objects we have built are not slow because our engineers lack imagination. They are slow because interstellar distance is in a different category from planetary distance. Mars is hard. Jupiter is far. Pluto is remote. Alpha Centauri is something else. It is not the next island across the sea. It is the sea itself, stretched until history becomes a unit of measurement. At 1% of light speed, a fast and still highly ambitious interstellar velocity, Alpha Centauri is roughly a 4-century journey. At 5% of light speed, it becomes an 80 to 90-year crossing, close enough that a mission might be conceived as a one-generation or edge-of-one-lifetime project if biology, acceleration, and resources cooperate. But most interesting targets are farther. A star 10 light-years away becomes 2 centuries at 5% of light speed, and a millennium at 1%. A system 40 light-years away becomes 8 centuries at 5% and 4,000 years at 1%. The boundary between a mission and a civilization appears very quickly. This is why science fiction invented faster-than-light travel, hibernation, wormholes, and jump drives. Without shortcuts, the stars are not unreachable, but they are temporally cruel. A probe can tolerate silence. A wafer-scale light sail can be accelerated by an external laser and sent on a flyby, as concepts like breakthrough starshot propose. That is not easy. Even gram-scale sailcraft at 20% of light speed require laser arrays, extreme pointing accuracy, dust survivability, and communications at photon-starved limits. But the payload is small, the mission is mostly robotic, and the craft does not need to sustain a society. A generation ship is different. It cannot be a chip. It must be a biosphere, a machine shop, a hospital, a school, a farm, a government, a memory system, a radiation shelter, a power plant, and a moral experiment, all sealed inside one moving structure. Here the first real counter-argument appears. Perhaps the ship does not need to be fast if it is self-contained enough. Earth itself is a closed world in many ways. It recycles water, it cycles carbon, it supports life over billions of years. Why not build a small Earth and let it travel? The answer is that Earth is not simply a closed box with plants in it. Earth is a planet-sized stabilizing machine with oceans, atmosphere, weather, geology, microbial diversity, chemical reservoirs, climate feedbacks, and sunlight spread across a surface area of more than 500 million square kilometers. It has enormous buffers. A generation ship has none of that scale. The smaller the closed system becomes, the faster its chemistry changes, and the less room there is for error. Biosphere 2 is not proof that closed ecology is impossible, but it is a useful warning. In the early 1990s, 8 people entered a sealed glass and steel habitat in Arizona designed to maintain a miniature biosphere. The system included biomes, agriculture, air, water, soil, and human occupants. It was not a crude experiment. It was ambitious, expensive, and carefully engineered. Yet oxygen fell from normal levels to around 14% after 16 months, enough to produce altitude-like symptoms. Part of the cause involved soil microbes consuming oxygen, and part involved carbon dioxide reacting with exposed concrete. Pollinating insects died. Some species collapsed. Certain insects and ants became dominant. Food production was difficult. Human social stress intensified. The lesson is not that a spacecraft would repeat those exact problems. The lesson is sharper. In a closed ecological system, a small, overlooked chemical or biological pathway can become mission scale because there is nowhere for the imbalance to dissipate. A generation ship would not rely on one elegant natural cycle. It would need layered systems, mechanical carbon dioxide removal, oxygen generation, plant growth, microbial waste processing, water recovery, trace contaminant removal, food production, atmosphere monitoring, and emergency reserve chemistry. In principle, this is better than asking plants alone to balance the air. In practice, it means the living world and the machine world become inseparable. If the hydroponic system fails, food and oxygen budgets change. If the filters fail, water chemistry changes. If power generation declines, lighting declines, plant productivity declines, oxygen production shifts, carbon dioxide control tightens, nutrition falls, labor capacity drops, maintenance slows, and more systems fall behind. The ship is not a set of independent devices. It is a single coupled organism made of metal, microbes, roots, circuits, and people. Now consider the vessel itself. A generation ship has to do what no spacecraft has ever done: remain operational not for decades, but across civilizational time. Voyager's survival is extraordinary precisely because it has lasted nearly 50 years. But Voyager is a small robotic probe. It does not have to feed anyone. It does not rotate for artificial gravity. It does not maintain a school system. It does not recycle thousands of liters of water every day or grow crops under electric light. It can shut down instruments to save power and still be a triumph. A generation ship cannot slowly become symbolic. Its life support systems have to work because people will be breathing the result. Every manufactured material aboard has a clock hidden inside it. Metals fatigue under cyclic stress. Polymers embrittle. Seals take compression set. Lubricants break down. Electronics suffer radiation-induced errors and long-term degradation. Coatings erode. Bearings wear. Welds develop stress concentrations. Adhesives outgas or crack. Sensors drift away from calibration. On Earth, this is normal. We repair, replace, inspect, recertify, and rebuild. Aircraft are safe because maintenance is constant. Nuclear reactors operate because components are monitored, replaced, and eventually retired. Space stations remain habitable because cargo ships arrive with parts, food, experiments, filters, and tools. The generation ship loses that safety net after departure. From then on, the spare parts inventory is not a warehouse. It is a countdown. A rotating habitat makes the problem concrete. Artificial gravity is usually proposed by rotating a large structure so that people inside feel a centripetal acceleration against the outer floor. The physics is straightforward, but the engineering ages. A ring rotating once or twice per minute creates repeated loads on structural members. Even if the stresses are well below failure limits, fatigue accumulates cycle after cycle. A ship rotating for centuries can impose tens or hundreds of millions of stress cycles on critical components. Fatigue failure often begins invisibly in tiny cracks at imperfections, joints, welds, bolt holes, or material inclusions. The crack grows slowly, then suddenly. Terrestrial aerospace engineering handles this through inspection and replacement. But a ship halfway to another star cannot order a new structural segment from a factory. It must either fabricate one, cannibalize another part of itself, reduce loads, abandon a module, or accept risk. Radiation makes material aging harsher. Outside Earth's magnetosphere, energetic particles are a persistent hazard. Outside the heliosphere, galactic cosmic rays remain a serious concern for long-duration travel. High-energy particles can pass through matter, damage electronics, displace atoms in crystal lattices, and create secondary radiation when they strike shielding. Heavy ions are especially troublesome because they leave dense tracks of ionization. For machinery, this means bit flips, sensor faults, semiconductor degradation, and changes in material properties. For biological tissue, it means DNA damage, cancer risk, cataracts, cardiovascular concerns, possible neurological effects, and germline mutations. Shielding helps, especially hydrogen-rich materials such as water or polyethylene, but shielding has mass. Mass demands propulsion energy. More shielding protects lives and electronics, but it also makes the ship harder to accelerate, harder to stop, and harder to build. This is a recurring structure in the generation ship problem. Every solution becomes a new mass, energy, or maintenance burden. Add thicker shielding, and the propulsion cost rises. Add redundancy, and the construction mass rises. Add spare parts, and the mass rises again. Add machine shops to make spare parts, and those machine shops require tools, calibration standards, feedstocks, power, replacement parts, and technicians. Add robots to perform maintenance, and the robots need maintenance. Add artificial intelligence to diagnose failures, and the computing substrate that runs the intelligence must be protected, powered, cooled, updated, and repaired. There is no magical top layer of the system that is exempt from entropy. The maintainer must also be maintained. This does not mean self-repair is useless. A serious generation ship would need it. The ship would need additive manufacturing, subtractive machining, recycling systems, diagnostic networks, modular replacement strategies, robotic inspection, and perhaps onboard materials synthesis. It would not be a sealed museum of spare parts. It would be a small industrial ecosystem. But modern industry is not one factory. It is a planet-scale web. A simple electronic sensor depends on purified elements, semiconductor fabrication, vacuum systems, photolithography, specialty chemicals, precision optics, software tools, metrology, and trained labor. A bearing depends on alloy production, heat treatment, grinding, inspection, lubricants, and contamination control. A membrane filter depends on polymer chemistry and manufacturing tolerances. To carry all of that capability in one ship is not merely to bring tools, it is to miniaturize an industrial civilization. The manufacturing bottleneck is one of the quietest and most dangerous barriers. Suppose the ship launches with superb systems and enough spare parts for a century. The first generations repair failures from stock. They still understand the original design. Documentation is fresh. Training pipelines are intact. Then rare components begin to run low. Some are replaced by locally manufactured versions that are almost as good, but not quite. Tolerances widen slightly. Pump impellers vibrate a little more. Valves seal a little less perfectly. Filters last a little less long. Lubricants made from recycled chemical stocks break down faster. Each substitution is rational in the moment. None is catastrophic. But the baseline drops. The next generation inherits a ship that is still alive, but less capable than it used to be. They normalize the decline because they have never known the original margin. This is how technological regression can happen without anyone becoming foolish. History already shows that knowledge can be lost when the institutions that keep it alive decay. Roman concrete was not lost because later people became stupid. It was lost because the supply chains, social conditions, building traditions, and tacit knowledge that made it useful were interrupted. Technical documents are not the same thing as living competence. A manual can describe how a reactor coolant pump works, but diagnosing a strange vibration at 3 in the morning often depends on experience. The sound of a healthy pump, the smell of an overheated bearing, the memory of a workaround that never made it into the official document. On a generation ship, tacit knowledge has to be transmitted across generations without interruption. A single plague, political crisis, educational collapse, or cultural shift can break a chain that took centuries to build. The strongest optimistic answer is that artificial intelligence could preserve knowledge perfectly. It could monitor every system, teach every generation, diagnose every fault, and design repairs beyond human capacity. This is worth taking seriously. Advanced autonomous systems would be essential for any plausible world ship. But the counterargument remains. An AI is not a ghost floating outside the ship. It runs on hardware, draws power, depends on sensors, stores memory and physical media, and learns from data that can become corrupted or incomplete. Its repair robots are machines. Its cameras get dust on them. Its processors age. Its training assumptions may fail when confronted with combinations of ecological drift, political stress, and degraded infrastructure never seen in the data that shaped it. The more central the AI becomes, the more its failure becomes civilization scale. The same question returns in a new form. Who maintains the maintainer, and with what tools? After 600 years, power is the ship's metabolism. Everything else depends on it. A generation ship cannot pause its energy use for a few decades until repairs are finished. Atmosphere, water, temperature, agriculture, communication, computation, medical systems, and lighting all draw from the power budget. Fission reactors are mature compared with most deep space power concepts, but long-duration reactor operation is limited by fuel, neutron damage, control mechanisms, coolant chemistry, and component aging. Breeder systems might extend fuel use, but increase complexity. Radioisotope sources are reliable because they have no moving parts, but their power falls with the half-life of the isotope. Fusion is attractive because the fuel density is high and the output could be enormous. Yet practical continuous fusion power plants remain an unfinished engineering achievement even on Earth, where technicians, supply chains, and test facilities are available. A generation ship powered by fusion assumes that one of humanity's largest technological problems has been solved so thoroughly that it can be sealed into a starship and trusted for centuries. Even if power is abundant, heat must go somewhere. Every watt used inside a closed vessel eventually becomes waste heat. In space, heat can only be rejected by radiation unless mass is expelled, and expelling mass is expensive. Radiators must be large, reliable, damage-tolerant, and clean enough to radiate efficiently. They will be struck by dust, degraded by micrometeoroids, stressed by thermal cycling, and possibly contaminated by leaks or deposition. If radiators lose capacity, internal temperatures rise. If internal temperatures rise, crops suffer, electronics degrade faster, coolant systems work harder, and power demand may rise. Heat management sounds less dramatic than propulsion, but for a sealed city in vacuum, it is existential. The outside medium is not completely empty. Interstellar dust is sparse, but at percent of light speed velocities, even tiny grains strike with destructive energy. A gram of dust at human speeds is harmless. A microgram at thousands of kilometers per second is not. The front of the ship would need sacrificial shielding, Whipple layers, ice or water mass, electromagnetic concepts for charged particles, and perhaps a forward cloud or bumper system. The largest dust impacts are rare, but a centuries-long voyage turns rare events into statistical possibilities. Again, the danger is not only one spectacular collision, it is cumulative erosion, pitting, secondary debris, weakening of exposed surfaces, and gradual loss of margin. The void is patient. It does not need to kill the ship in one blow. Now bring humans aboard. A world ship is not a cargo container. It is a reproductive society. The founding population must be large enough to avoid dangerous inbreeding and preserve genetic diversity, but small enough for the ship to carry, feed, shelter, and govern. Published estimates vary widely because they depend on assumptions. Random mating or chosen mating, stored embryos or none, strict genetic management or cultural autonomy, mutation rate, radiation dose, acceptable inbreeding, and mission duration. Simple models can produce surprisingly small numbers under idealized conditions. More realistic scenarios push the required population into the thousands, and some proposals argue for tens of thousands if social behavior and long duration are included. The scientific caution matters here. There is no single magic number. There is a range of risk shaped by biology and culture. Genetic drift does not care about the nobility of the mission. In a finite population, allele frequencies change by chance. Rare variants disappear. Recessive harmful variants can become more common in pairings as relatedness increases. Radiation adds another input by raising the mutation burden, especially if shielding is imperfect and germ cells are exposed over generations. Natural selection might remove some harmful mutations, but selection operates through illness, infertility, miscarriage, and death. That is not a clean engineering feedback loop. It is suffering distributed across families. Stored embryos, sperm, eggs, or sequenced genetic libraries could reduce risk, but they add cryogenic storage, reproductive technology, medical expertise, and ethical governance burdens. A frozen genetic reserve is only useful if the freezer works, the records survive, the medical system remains competent, and the society still agrees to use it. The radiation problem is not only cancer. Chronic exposure beyond Earth's protective magnetic field can affect tissues in ways that are still under study. Nervous system risk, cardiovascular risk, cataracts, immune changes, reproductive effects, and developmental concerns. NASA and other space agencies treat space radiation as one of the major unresolved hazards for long-duration human exploration, even for missions to Mars measured in months or years. A generation ship asks the same biology to endure not one mission, but an inherited environment. Children could be conceived, gestated, born, and raised under a radiation regime no human population has ever experienced. Shielding can reduce the dose, and habitats can place water, food stores, fuel, and waste around living areas. But deep shielding for an entire city-sized vessel is heavy. A more plausible design might shield storm shelters and sleeping quarters more heavily than open spaces, accepting a managed lifetime dose rather than eliminating exposure. That is not impossible, but it is not the effortless radiation immunity that fiction often assumes. The ecosystem must also reproduce itself. Food production is not just a greenhouse with tomatoes under LED lights. It is a controlled ecology with crops, microbes, nutrients, pests, pathogens, pollination or manual substitutes, waste processing, trace minerals, water chemistry, and genetic diversity. Hydroponics and aeroponics are efficient, but they depend on pumps, lights, sensors, membranes, sterilization, nutrient formulations, and energy. Soil-based agriculture provides richer microbial buffering, but soil is heavy, complex, biologically unstable in small volumes, and hard to reset if pathogens dominate. A generation ship might use both: controlled plant growth, microbial bioreactors, algae systems, fungi, perhaps cultured protein, and stored reserves. But every food system needs renewal. Seeds age, microbial communities evolve, plant pathogens adapt, nutrient balances drift. A closed agricultural system is vulnerable to a version of the Irish potato famine problem. On Earth, crop failure can be softened by trade, crop substitution, breeding programs, wild relatives, external seed banks, and global agriculture. On a ship, a staple crop failure is not a local disaster. It is a ship-wide shock. If a pathogen evolves in the closed environment and overcomes the resistance of a genetically narrow crop variety, the crew cannot import new seed from a continent away. They can use stored varieties if they remain viable, gene editing if equipment and expertise survive, chemical controls if feedstocks exist, or diet shifts if alternatives can scale. Each fallback depends on another system. Food security in a world ship is not the ability to grow lettuce for a year. It is the ability to maintain a resilient food civilization for centuries inside a finite container. Water seems easier because water is conserved. Yet even water becomes complicated. The ship can recycle urine, humidity condensate, wash water, and agricultural runoff. The International Space Station already recovers much of its water, proving that high recovery is possible in orbit. But high recovery is not perfect recovery. Filters foul. Membranes degrade. Trace contaminants accumulate. Pharmaceuticals, Endocrine disruptors, metal ions, cleaning agents, microbial byproducts, and sterilization residues have to be removed or transformed. On Earth, a water treatment plant sits inside an open chemical economy. A generation ship's treatment plant sits inside the same closed inventory it is trying to protect. The system must not only recycle water, but also recycle the capacity to recycle water. Air is even more psychologically immediate. Oxygen must remain in a safe range. Carbon dioxide must be controlled not only to avoid death, but to preserve cognition and long-term health. Trace gases from materials, equipment, plants, microbes, and human activity must be monitored. A small leak, a slow reaction with structural material, a microbial bloom, or a sensor drift can become dangerous if the system believes the air is safer than it is. In a closed habitat, atmosphere is shared fate. One person's fire, solvent release, infection control error, or agricultural imbalance becomes everyone's environment. Then there is gravity. Humans evolved under 1G. Long-term weightlessness damages bone, muscle, cardiovascular function, balance, vision, and fluid distribution. A generation ship cannot simply let people float for centuries. Artificial gravity through rotation is the most plausible known method, but it has costs. Large radius to reduce motion sickness, rotating seals or whole structure rotation, structural mass, fatigue loads, docking complications, and possible psychological effects of living in a curved, spinning world. If the rotation rate is high, the Coriolis effect becomes noticeable when people move. If the radius is large, the ship becomes enormous. If different sections rotate separately, mechanical interfaces become complex. The body demands gravity. The machine pays for it. Medicine aboard a generation ship must become a complete, isolated medical civilization. It must handle births, dentistry, trauma, infection, cancer, genetic disease, mental illness, aging, reproductive technology, surgery, chronic disease, and public health. It must do this with finite pharmaceuticals, finite reagents, finite imaging equipment, finite prosthetics, finite sterile materials, and a finite number of trained specialists. Drug synthesis may be possible for some compounds, but not all. Antibiotic resistance can evolve in closed environments. Viral and bacterial pathogens can move through a dense population. If the population is small, losing even a few key physicians, surgeons, or microbiologists during a crisis can create knowledge gaps with consequences that last generations. A hospital on Earth is backed by a planet. A hospital on a generation ship is backed by a storage room and a training program. Social life may be the most underestimated system of all. It is tempting to speak of a generation ship as if it were a machine containing people, but it would really be a society whose mechanical survival depends on political continuity. People aboard the ship would need governance, conflict resolution, law, education, reproduction policies, labor allocation, resource rationing, psychological care, cultural meaning, and mechanisms for adapting without destroying the mission. The founding generation may believe in the purpose. They chose the risk, or at least participated in the decision. The arrival generation may see the destination ahead. But the middle generations are born into a moral puzzle. They are alive because someone else chose a mission they cannot leave, toward a world they may never see, maintained by labor they cannot fully refuse. That is not just a logistical issue. It is an ethical pressure built into the architecture. The strongest defense is that human cultures have endured hardship before. Monastic orders, maritime communities, Arctic settlements, island cultures, and long-lived civilizations have preserved values across centuries. People are meaning-making animals. A ship society could develop rituals, education, art, ceremonies, kinship structures, and a sacred sense of mission. It might not experience the voyage as imprisonment. It might experience it as home. This counter-argument should not be dismissed. People born on a ship would not necessarily grieve open landscapes they never knew. They might love their corridors, gardens, windows, and rotating sky. They might build a culture suited to the vessel. But culture can stabilize or destabilize. A mission religion can preserve purpose, or it can reject technical reality. A hierarchy can allocate labor, or it can become oppressive. A democracy can legitimize hard choices, or it can vote to stop maintaining systems whose benefits lie centuries ahead. Social design is as critical as hull design, and less predictable. Consent becomes sharper across generations. The founders may consent to departure. Their descendants cannot consent to being born into the mission. Of course, no child chooses the world into which they are born. Children on Earth do not consent to their planet either. But Earth offers exits, variation, and open futures on a scale a ship cannot. A person on a world ship cannot move to another continent, choose another climate, escape the political system entirely, or wait for supply from outside. Their society's mistakes become their atmosphere. Their ancestors' engineering decisions become their biology. A generation ship therefore asks whether one generation has the moral right to impose a centuries-long survival obligation on descendants for a destination none of them requested. That question is not answered by physics, but it belongs beside the physics. Population size interacts with politics. A vessel with a few hundred people may be easier to feed and shield, but genetically and socially fragile. Everyone knows everyone. Conflict can become personal and inescapable. A vessel with tens of thousands of people gives genetic diversity, labor diversity, and cultural resilience, but increases mass, energy demand, food systems, waste processing, living volume, governance complexity, and the scale of potential conflict. There is no free population number. Small ships risk biological and institutional fragility. Large ships risk construction and maintenance impossibility. Somewhere in between may be a viable window, but that window depends on propulsion, mission duration, radiation shielding, automation, ecology, and ethics at the same time. Now step back and look at the mathematics of failure. A generation ship is not judged by whether one subsystem is highly reliable. It is judged by whether all critical subsystems remain sufficiently reliable together over the full duration. Suppose each essential system has an excellent chance of functioning over a decade. If there are many such systems, the chance that all of them remain within mission limits falls faster than intuition expects. Reliability compounds. A ship does not need every pump to fail. It needs the wrong set of failures to occur faster than repair capacity can recover. A small oxygen issue combined with a crop disease, combined with a spare parts shortage, combined with a political crisis, can be more dangerous than a dramatic single disaster, because each problem reduces the ability to solve the others. In engineering, redundancy is the normal answer. Build 3 of everything. Separate systems physically. Use different designs so one flaw does not disable all copies. Keep reserves. This works, but redundancy is not infinite. Each backup has mass. Each backup ages. Each backup needs maintenance. When one system fails, the backup becomes primary. When the backup fails, the margin is gone. A world ship hundreds of years into flight may still function, but with its redundancy slowly spent, fewer spare filters, fewer pristine modules, fewer trained experts, fewer high-quality bearings, fewer uncontaminated biological reserves, fewer reactor components, fewer uncorrupted archives. The ship's official status may be operational long after the safety margin has been consumed. This is where normalization of deviance becomes lethal. A founding crew might treat a 2% drop in crop yield as alarming. A later generation that has never seen the original yield may call it normal. A slightly wider carbon dioxide fluctuation becomes normal. More frequent pump rebuilds become normal. A water taste issue becomes normal. A radiation shelter closure because of material degradation becomes normal. The baseline moves downward slowly enough that no one moment feels like a collapse. The ship does not fail like a bomb. It ages like an empire. It forgets the difference between acceptable and inherited. Could the mission avoid centuries by going faster? This is the most scientifically honest path. Speed does not only reduce impatience, it reduces exposure time to every cumulative risk. A 90-year mission to Alpha Centauri is difficult in a way that a 1,000-year mission to a farther star may be effectively prohibitive. Faster transit compresses the window for material degradation, social drift, genetic drift, ecological instability, and radiation exposure. That is why high-energy propulsion matters so much. Not because it is glamorous, but because time is corrosive. A fast mission can be designed as a spacecraft. A slow mission becomes a civilization sealed inside a reliability experiment. But fast crewed travel is energetically brutal. Chemical rockets are irrelevant for interstellar velocities because the rocket equation punishes any vehicle that carries its own propellant. Nuclear thermal propulsion could transform travel within the solar system, but it does not push a massive world ship to percent of light speed cruise. Nuclear pulse concepts like Project Orion are among the more physically grounded high-thrust ideas. Uncrewed interstellar studies, such as Project Daedalus, imagined fusion-based probes with enormous fuel masses and flyby profiles, not easy human settlements. Beamed sails may work for gram-scale probes, but scaling a laser-pushed sail from a wafer to a city is not linear in practical terms. The power, optics, heat, sail stress, beam pointing, acceleration limits, and deceleration challenge become monstrous. Every propulsion concept that stays inside known physics runs into one of two walls: energy or time. Deceleration is often forgotten. Reaching a target system at 5% of light speed is not the same as settling there. A flyby probe can rush through, take data, and transmit. A generation ship must slow down. If it carries propellant for braking, it must accelerate that propellant during departure, increasing mass and energy. If it uses a magnetic sail, electric sail, or interaction with the stellar wind and interstellar medium, the braking system must be large, reliable, and effective over long periods. If it uses a laser from the origin, the beam divergence and pointing problem across light years becomes severe. If it relies on infrastructure already at the destination, then the mission requires a previous mission that somehow built it. Arrival is not a cinematic moment where engines stop at the edge of a blue planet. Arrival is another major engineering campaign. The destination itself may not cooperate. A star system that looks promising from Earth may reveal no habitable planet, no easily accessible volatiles, no stable orbit for the habitat, too much flare activity, too little metal-rich material, or a biosphere incompatible with human biology. For a robotic probe, a disappointing target is still scientifically valuable. For a generation ship, it is existential. The vessel must be prepared not only to arrive, but to survive if the destination is not what its ancestors hoped. That means it must remain a viable space habitat after arrival, perhaps for decades or centuries more. While scouts survey, factories begin processing local materials, and the population decides whether settlement is safe. The voyage may end before the dependence on the ship ends. One powerful alternative is to avoid sending living adults. Send embryos, gametes, artificial wombs, robotic caretakers, and archives. This seed ship concept reduces mass, food needs, psychology, social conflict, and life support burden during transit. It is one of the strongest counterarguments to the classic generation ship. But it transfers difficulty elsewhere. Cryogenic storage over centuries must be reliable. Artificial gestation and childhood care by machines must work not as laboratory demonstrations, but as a complete substitute for human society. The first generation at arrival would be raised by systems whose designers died centuries earlier. They would need language, ethics, emotional development, technical education, and a culture strong enough to survive in an alien system. A seed ship solves some closed ecology problems by postponing humans, but it creates an even stranger moral and developmental problem. A civilization manufactured at the destination by machines. Another alternative is the purely robotic path. Send machines, not people. Send self-replicating probes or automated factories that use local asteroid material to build more probes and prepare infrastructure. This is physically more plausible in some respects. Machines can be smaller, more tolerant of radiation, easier to duplicate, and less ethically fraught than multi-generational human confinement. But self-replication is not a magic phrase. A factory that can reproduce itself from raw asteroid material is an industrial civilization in compact form. It must mine, refine, fabricate, assemble, test, repair, and control quality using unknown local materials. It must avoid runaway errors and resource traps. It must be robust to radiation, dust, software corruption, and unpredictable geology. Robotic expansion may be more plausible than generation ships, but it is not the same as carrying a human society across the void. A third alternative is local ambition. Do not cross the stars until we have mastered living away from Earth within our own solar system. Build rotating habitats, closed agriculture, radiation shelters, autonomous industry, asteroid mining, lunar and Martian settlements, and multi-century institutions near home first. This is not romantic, but it is scientifically sensible. The solar system is a laboratory with rescue possibilities, communication delays of minutes to hours, abundant raw material, and gradients of difficulty. If humanity cannot maintain a closed habitat for centuries between Earth and Mars, it has no business sending one into interstellar darkness. A true generation ship would not be the beginning of space colonization. It would be the late result of a long apprenticeship in artificial worlds. This reframes the topic. The question is not, can we build a generation ship? The sharper question is, what must a civilization become before a generation ship stops being a fantasy and becomes a risk it can ethically defend? It must become capable of closed ecological stability beyond anything demonstrated. It must develop materials and structures that can survive centuries of radiation, fatigue, and repair. It must build autonomous industry that can reproduce critical components from finite or locally gathered resources. It must preserve technical knowledge across generations. It must govern reproduction without tyranny, allocate labor without caste, maintain purpose without fanaticism, and protect individual dignity inside a mission whose purpose outlives every individual aboard. The ship is not only a machine, it is a test of civilization. There is also a language trap in the phrase self-sustaining. On a planet, self-sustaining often means a community can produce food, maintain shelter, and trade or adapt. On a generation ship, self-sustaining must mean something much stricter. Closed material cycles, repair of repair systems, preservation of genetic and microbial diversity, continuous education, long-term governance, and enough energy to compensate for every local entropy decrease by dumping waste heat into space. A ship can be self-sustaining for 10 years and still be hopeless for 500. The duration is not an accessory to the claim. It is the claim. The same applies to closed loop. A nearly closed loop may be excellent for a space station resupplied by Earth. A 98% water recovery system is a triumph when cargo vehicles can bring replacement filters. But over centuries, tiny losses and contaminant accumulation matter. A 99.9% closure rate may sound perfect until the missing 0.1% runs for thousands of cycles. The gap between nearly closed and closed is the gap through which the mission's future leaks. Some losses can be replaced by initial reserves, some by recycling, some by using matter from interstellar dust or target system resources after arrival. But during the cruise phase, the ship lives inside its inventory. The inventory is fate. At this point, the pessimistic argument can go too far. It would be wrong to conclude that generation ships are impossible because our present technology cannot build one. Many ideas that once looked impossible became routine after the right infrastructure existed. Oceanic voyages, heavier than air flight, nuclear reactors, space probes, genome sequencing, and global communications all required layers of technology that earlier generations could not imagine. A civilization centuries ahead of us may have materials with self-healing properties, closed ecological systems tested for thousands of years, engineered microbes tuned for nutrient cycles, robust artificial intelligence, mature fusion power, and space industry vast enough to assemble habitats from asteroid material. We should not measure all futures with the ruler of 2026. But the optimistic argument also fails when it treats future technology as a blank check. Technology can change coefficients. It can improve reliability, reduce mass, increase energy efficiency, automate maintenance, and widen margins. It cannot make a massive ship reach light speed. It cannot make radiation vanish. It cannot make finite resources infinite. It cannot make a closed system immune to drift. It cannot make descendants automatically consent to ancestral missions. It cannot make a 1,000-year institution easy because a database exists. Future technology may move the boundary between plausible and reckless. It does not remove the boundary. The most defensible conclusion is therefore narrow and uncomfortable. Generation ships to the nearest stars, with transit times perhaps under a few centuries, may be a legitimate subject of serious long-term engineering thought if propulsion improves, if closed habitats are proven over very long durations, and if the ethical framework is confronted honestly. Generation ships lasting many centuries or millennia are much harder to defend, not because one dramatic obstacle forbids them, but because too many slow processes have too much time to converge. The longer the cruise, the more the ship becomes an entropy experiment with a human population inside. A 1,000-year mission is not 1,000-year missions lined up. It is a different category of risk. This is why the true science of generation ships is less like rocket science and more like ecology, reliability engineering, population genetics, social philosophy, materials science, and theology braided together. It asks how long a technical culture can remember itself. It asks how small a biosphere can be before it becomes unstable. It asks how much radiation a lineage can absorb. It asks how many spare parts are enough when every part is aging. It asks whether a society can be born in a corridor and still feel human. It asks whether exploration can justify inherited obligation. These are not questions a better engine alone can answer. Imagine again the child in the sealed city. The child walks past gardens grown under lamps, past water tanks that shimmer behind transparent shields, past machines whose parts have been replaced so many times that no one remembers the original manufacturer. Somewhere behind a wall, a reactor hums, or a fusion chamber pulses, or stored energy flows through superconducting lines. In a classroom, a teacher explains Earth, blue oceans, open weather, mountains, insects, rain that fell from an actual sky. The children listen with curiosity, not nostalgia. Earth is not home to them. The ship is home. And that may be the most haunting possibility of all. A generation ship that survives would not preserve Earth unchanged. It would create a new branch of humanity, adapted culturally and perhaps biologically to metal, recycling, rotation, and inherited purpose. If such people arrived at another star, would they still want what the founders wanted? Would they step onto a planet eagerly? Or would they fear open horizons? Would gravity feel natural or violent? Would soil smell like life or contamination? Would they see a planet as freedom, or as an uncontrolled ecosystem full of pathogens, weather, and uncertainties? The mission planners imagine arrival as fulfillment. The arrival generation might experience it as exile from the only world they have ever known. That possibility does not make the mission wrong, but it reveals how poor our simple narratives are. The destination is not simply a promised land. It is a cultural shock waiting centuries in the future. There is a profound reversal here. We often imagine a generation ship as a way to keep humanity continuous across interstellar distance. But a successful generation ship may require discontinuity. The shipborne society may need to become different from the launching culture in order to survive. It may need stricter resource ethics, different family structures, different aesthetics, different concepts of privacy, property, childhood, work, risk, and death. Too much attachment to Earth normal assumptions might be dangerous. The descendants may survive precisely because they stop being the people the founders expected. In that sense, the generation ship is not a bridge preserving one civilization. It is a seed that mutates in transit. This is also why the generation ship is such a powerful mirror. It takes problems we already have on Earth and removes the buffers. Sustainability becomes literal. Education becomes life support. Public trust becomes atmosphere. Maintenance becomes morality. Waste becomes resource. Political incompetence becomes oxygen risk. Inequality becomes structural danger. A society that cannot plan beyond a few election cycles, cannot maintain infrastructure, cannot protect scientific institutions, cannot manage ecosystems, and cannot distribute burdens fairly, would not become wiser by sealing itself inside a vessel. The ship would amplify its weaknesses. The first requirement for building a world ship may be learning how to keep a world. None of this diminishes the grandeur of the idea. If anything, it makes it larger. A generation ship is one of the most extreme artifacts intelligence could attempt. A vessel that carries not only bodies, but continuity. Not only equipment, but culture. Not only life, but the conditions that make life repair itself. It is a monument to the refusal to let distance end the story. Yet the monument stands under a law older than stars. Entropy is not evil. It is not trying to kill the crew. It is simply the statistical direction in which unmanaged systems move. The ship survives only by spending energy to make local order again and again and again, in pipes, cells, schools, fields, databases, friendships, and laws. So the final answer is not the easy one. The generation ship is neither a guaranteed destiny nor a foolish impossibility. It is a narrow, dangerous, ethically charged possibility whose feasibility shrinks rapidly with duration. The nearest stars might be within reach of a civilization far more capable than ours, if it can move fast enough to keep the voyage short and build habitats reliable enough to endure the crossing. The farther stars, the ones that demand millennia, belong to a harsher regime where every weakness has time to surface and every repair system becomes part of the problem it solves. The enemy is not the void alone. The enemy is the long multiplication of small failures. When science fiction shows a generation ship, it often waits for the dramatic event, the mutiny, the meteor strike, the reactor explosion, the revelation that the passengers forgot the mission. Reality may be quieter. The most realistic failure might be a crop that yields 2% less. A bearing replaced with a weaker alloy. A training program shortened during a crisis. A sensor recalibrated against an aging standard. A pathogen that no longer responds to the old control method. A child born with a higher mutation burden. A law changed to solve an immediate problem while weakening a long-term safeguard. Not one disaster. 1,000 small negotiations with decline. And yet, somewhere inside the hard arithmetic, there remains a human reason the idea refuses to die. We are the species that crosses difficult spaces. We crossed ice, ocean, desert, mountain, and orbit. We build vessels because horizons offend us. We preserve stories because death offends us. The stars are the largest horizon we know, and a generation ship is the most stubborn answer we have imagined to the fact that we cannot reach them quickly. The universe may not forbid the answer, but it demands honesty as the price of even considering it. If humanity ever launches such a ship, it should not do so because it believes the voyage will be romantic. It should do so only after centuries of practice in closed habitats, after proving that ecosystems can remain stable, that machines can reproduce their own precision, that radiation can be managed, that populations can remain healthy, that knowledge can survive institutional change, and that the people born aboard will be treated not as fuel for a mission, but as citizens of the only world they know. Anything less would be not exploration, but abandonment disguised as courage. For now, the generation ship remains suspended between dream and warning. It shows us the stars, and then asks what time will do to anyone trying to reach them slowly. It shows us that the distance to Alpha Centauri is not only 4 light years. It is thousands of maintenance cycles, millions of breaths, countless cell divisions, hundreds of political decisions, and an unbroken chain of competence stretching farther than most human institutions have ever lasted. The true barrier between the stars is not a wall. It is a duration. And duration is where entropy hides. There is a way to make the argument more concrete. Think of a generation ship as having 3 clocks. The first clock is the travel clock, determined by distance and velocity. This is the clock everyone notices. 4 light years at 1% of light speed is 4 centuries. 40 light years is 4 millennia. The second clock is the engineering clock, determined by the lifetime of components, materials, power systems, seals, radiators, sensors, bearings, pressure vessels, and software. The third clock is the human clock, determined by memory, culture, population genetics, childhood, politics, education, and meaning. A mission succeeds only if all 3 clocks remain compatible. It is not enough for propulsion to deliver the ship in 800 years if the engineering clock runs out after 300. It is not enough for machinery to survive 500 years if the social clock fractures in 200. It is not enough for a society to stay loyal if the radiation clock has already undermined fertility and health. The brutal part is that these clocks are not independent. When one runs fast, it speeds up the others. For example, a power shortage is not simply an engineering fault. It becomes an agricultural problem because grow lights and pumps must be rationed. It becomes a medical problem because refrigeration and sterilization become harder. It becomes a social problem because rationing must be justified. It becomes an educational problem because more labor is diverted from training into emergency maintenance. It becomes a genetic problem if malnutrition reduces fertility or childhood development. In the opposite direction, a social breakdown is not merely political. It becomes engineering risk because maintenance schedules may be ignored, expertise may be politicized, and unpopular but necessary repairs may be delayed. A generation ship is a coupled system in which no failure remains politely inside its own category. The launch phase alone would demand a civilization that already lives comfortably in space. A vessel of hundreds of thousands or millions of tons cannot be launched from Earth by rockets in any ordinary sense. It would almost certainly be built in orbit or in cislunar space from material mined from the Moon, asteroids, or other low-gravity bodies. That means the generation ship presupposes an enormous prior space economy. Mining, refining, construction yards, radiation-safe worker habitats, autonomous logistics, quality control, propulsion tugs, orbital traffic management, and energy infrastructure on a scale far beyond anything humanity currently possesses. This matters because people often imagine the generation ship as a single heroic project. It would actually be the visible tip of a mature industrial system already spread through the inner solar system. If that supporting civilization does not exist, the ship cannot be built. If that supporting civilization exists, then the ship is no longer humanity's first step outward, but one of the last steps after a long technological transformation. Even choosing a destination is harder than fiction suggests. A star that looks attractive from Earth may be revealed by later telescopes to have no suitable planets. A planet in the habitable zone may have a runaway greenhouse, a frozen surface, a toxic atmosphere, unstable obliquity, lethal flaring from a red dwarf, or a biosphere whose chemistry is dangerous to terrestrial organisms. The longer the mission planning timeline, the more the target knowledge improves. But the more launch gets delayed, the faster the launch, the greater the uncertainty. A generation ship would probably need to be flexible enough to become its own permanent settlement if the target disappoints. That means the ship cannot be designed merely as transportation. It must be designed as a destination in itself. This point changes the ethical equation. If the ship is only a vehicle, the middle generations are passengers trapped inside a bridge to someone else's future. If the ship is a world, then the middle generations are citizens of a legitimate society whose value does not depend entirely on arrival. The latter is more humane, but also more demanding. A world must provide beauty, not only survival. It must provide choices, not only duties. It must provide spaces where people can love, grieve, rebel, create, and waste time without being treated as inefficient parts in a mission machine. A generation ship designed only by engineers would fail this test. So would a generation ship designed only by philosophers. It has to be both a closed technical system and a culture worth inhabiting. Artificial gravity illustrates the design conflict between biology and architecture. If the habitat rotates too quickly, people may suffer disorientation as the Coriolis effect bends the apparent motion of objects and fluid inside the inner ear. If the radius is too small, moving the head can produce strange accelerations. If the radius is large enough for comfort, the structure becomes massive. A torus hundreds of meters across, or even kilometers across, may be desirable for a large population, but such a structure carries enormous material cost and complex stress management. One could choose lower gravity to reduce structural loads, perhaps Mars-like gravity or lunar gravity. But no one knows whether children conceived and raised for generations under partial gravity would develop normally. We have data from microgravity, some from partial simulations, but not a century-long human experiment at 0.38 G or 0.16 G. A generation ship cannot afford to discover after launch that its chosen gravity level quietly damages reproduction or development. This is one reason a serious program would need precursor habitats. Not short space stations, not 6-month analog missions. Real multi-generation settlements in space, perhaps around the moon or in free orbit, where rotation, ecology, governance, radiation shielding, and reproduction can be studied with the option of rescue. That sounds uncomfortable because it means the road to a generation ship is not a single technological leap. It is centuries of rehearsal. The rehearsal would be expensive, morally complex, and slow. Yet without it, the interstellar mission would be an experiment performed on descendants who cannot opt out. A civilization that refuses the rehearsal because it is too slow has not earned the right to attempt the voyage. The ship's archives would be another fragile organ. People imagine storing all human knowledge as if storage were simple. In raw volume, it is easier than ever. But knowledge is not only bits. It is formats, context, pedagogy, language, assumptions, and institutional use. A file from 500 years ago may be unreadable if the software ecosystem is gone. A scientific paper may be incomprehensible if the educational ladder needed to understand it has collapsed. A legal archive may be irrelevant if the society's values have shifted beyond recognition. To preserve knowledge, the ship must preserve not only databases, but active traditions of interpretation. Mathematics, physics, medicine, agriculture, history, ethics, and engineering must remain living disciplines, not dead libraries. That requires teachers, students, experiments, laboratories, debates, errors, corrections, and time protected from the constant pressure of maintenance. This protected time may be one of the most difficult resources to preserve. A stressed ship will always be tempted to cut the future to save the present. Shorten apprenticeships, delay basic research, skip documentation, cannibalize laboratory equipment for parts, reduce arts and humanities because they do not fix the oxygen system. In a crisis, these choices may be necessary. Repeated across generations, they impoverish the culture's ability to understand itself. A purely survival-oriented ship may become less capable of survival because it has sacrificed the slow institutions that produce competence and meaning. The paradox is cruel. A generation ship must be disciplined enough to survive emergencies, but generous enough to preserve non-emergency life. There is also the problem of law. On Earth, law is backed by territory, courts, police, tradition, public legitimacy, and ultimately the fact that people can sometimes leave one jurisdiction for another. On a world ship, there is no outside jurisdiction. The government controls access to air, water, food, space, reproduction policy, and dangerous equipment. Even a benign government holds extraordinary power because survival infrastructure is centralized. Preventing tyranny would require constitutional design unlike anything on Earth, distributed control of life support systems, transparent resource accounting, rights that survive emergencies, and mechanisms for replacing leadership without endangering the ship. Yet too much fragmentation could paralyze necessary decisions. A generation ship needs authority strong enough to act, but limited enough not to become a prison state. That balance has challenged human societies under far easier conditions. Conflict over reproduction may be unavoidable. Population must stay within ecological limits. Too many births strain food, space, water, education, and medical care. Too few births weaken labor capacity, genetic diversity, and cultural continuity. Some form of reproductive planning would be necessary. The question is, how coercive it becomes. A society could use incentives, cultural norms, transparent genetic counseling, lottery systems, or legal limits. Each option has moral costs. A crisis that reduces population may create pressure to compel births. A resource shortage may create pressure to forbid them. Both choices enter the most intimate parts of human life. The ship's survival may depend on decisions that would be ethically explosive on Earth. The same is true of labor. Critical roles cannot simply be left vacant because no one feels called to them. Someone must maintain reactors, farms, filters, hull sensors, medical systems, archives, and governance structures. A free society aboard the ship may still need to steer education toward mission-critical work. But if children are assigned careers too early, society becomes rigid. If everyone is free to choose without regard to need, essential skills may be undersupplied. Automation can reduce this pressure, but not erase it. A generation ship therefore raises a question that modern societies often avoid. How does a community preserve individual freedom when the margin for collective failure is small? Psychology aboard the ship would not be a temporary crew support issue. It would be a civilizational substrate. Depression, anxiety, resentment, claustrophobia, status conflict, grief, and alienation are not side effects when they affect the people who maintain air and food. The middle generations may need a culture that frames their lives as complete, not as waiting rooms for arrival. That culture may include art, religion, civic mythology, science education, festivals tied not to seasons outside, but to mission cycles, and perhaps simulated landscapes that give the nervous system something like open space. Virtual reality could help, but again, it relies on hardware and power. A projected forest is not a forest if the projector fails. Some might argue that post-biological intelligence avoids these problems. Upload minds, send machines, leave flesh, farming, reproduction, and psychology behind. This is the most radical counterargument. If minds can be instantiated in durable computational substrates, then mass falls, life support shrinks, biological radiation risk changes, and subjective time may even be managed differently. But this answer depends on assumptions far beyond established science. We do not know whether mind uploading is possible, whether a digital copy would be a continuation of a person or a new entity, whether such systems could remain sane or coherent across centuries, or whether computational hardware can be made indefinitely self-repairing in deep space. Post-biological travel may one day redefine the problem, but it cannot be used as a proven solution for generation ships carrying human beings. A related idea is suspended animation. Reduce metabolism, slow aging, and let passengers sleep through the centuries. Nature gives partial inspiration, hibernation, torpor, cryptobiosis in tiny organisms, and preservation of embryos. But no mammal can be frozen, stored for centuries, and revived as an adult with memory and identity intact using current biology. Even if reversible human torpor becomes possible, maintaining thousands of bodies in suspended states would require energy, monitoring, repair of cellular damage, and extremely reliable revival systems. A sleeper ship might reduce social problems during cruise, but it concentrates risk into cryogenic or metabolic control systems. One prolonged power failure, one design flaw, one unnoticed molecular damage pathway, and the sleeping population becomes unrecoverable. The dream of sleep is also a dream of trusting machines completely. The more we examine alternatives, the more one pattern emerges. Every plausible workaround reduces one dimension of the problem by increasing another. Robotics reduces life support but increases autonomy demands. Cryosleep reduces social drift but increases biomedical and system reliability risk. Embryo ships reduce cruise ecology but create unprecedented childhood and consent problems. Faster propulsion reduces time but increases energy, acceleration, shielding, and braking demands. Larger populations improve genetics but increase mass and ecology. Smaller populations reduce mass but increase fragility. There is no single clever escape. There is a trade space, and the trade space is unforgiving. This trade space matters for the public imagination because it changes what counts as success. A vessel that reaches Alpha Centauri with a thriving population after 90 years would be one of the greatest achievements in the history of intelligence. A vessel that attempts a 4,000-year journey to a distant system may be less an act of exploration than an act of faith that future generations can keep solving compounded problems indefinitely. Both are called generation ships, but they do not belong to the same category. The phrase hides too much. Duration must be the first number spoken because duration determines everything else. There is a painful analogy with aging. A young body can heal small injuries quickly. An older body may survive the same injury, but recover more slowly. Multiple small problems that would have been trivial in youth can combine into a dangerous cascade. The generation ship ages in the same way. Early failures are repaired with abundant spares and strong institutions. Later failures occur in a system already carrying scars. The ship's resilience is not fixed. It is consumed, rebuilt, consumed again, and gradually transformed. A mission plan that treats the ship in year 600 as the same vehicle that launched in year 1 is not a mission plan. It is denial. What would a better design philosophy look like? It would begin by assuming decay, not perfection. The ship would be modular, able to lose parts without dying. It would use simple systems where possible, not only elegant, advanced ones. It would favor maintainability over peak efficiency. It would store raw materials, not only finished spares. It would preserve multiple independent food pathways rather than one optimized agriculture system. It would teach repair as a civic virtue. It would keep its laws legible and its resource accounting transparent. It would avoid single points of failure even when those single points are astonishingly sophisticated. It would treat beauty, education, and social legitimacy as life support systems, because for multi-century survival, they are. Even then, the ship would need humility built into its mission. It might not promise a planet. It might promise a search. It might arrive and remain orbital. It might split into habitats around asteroids. It might treat terraforming as a distant possibility rather than an assumption. It might send probes ahead decades before arrival to refine plans. It might carry enough propulsion margin to redirect within the target system, but not enough to choose a completely different star. Every plan would need margins so large that they appear wasteful from the viewpoint of short missions. In a generation ship, margin is not inefficiency. Margin is mercy. The final controversy, then, is not whether humans are brave enough. Humans are often brave enough for things they do not fully understand. The controversy is whether bravery is the right virtue. A generation ship requires patience, competence, restraint, and an unusual form of love for people who do not yet exist. It asks the founding civilization to spend enormous resources on descendants who may reject its values. It asks the crew to maintain a world whose purpose may change. It asks engineers to design for failures they cannot predict, and ethicists to protect freedoms inside a sealed survival machine. Courage may launch the ship. Only humility keeps it alive. A serious design would probably separate the ship into layers of confidence. At the center would be the protected core: command archives, medical reserves, genetic libraries, critical manufacturing tools, and the most heavily shielded living spaces. Around that would sit the working biosphere: farms, water systems, waste processors, workshops, schools, clinics, and communal spaces. Farther outward would sit sacrificial mass: tanks, ice, raw materials, shielding, radiators, dust bumpers, and structures expected to erode. This layered design would be rational, but it would also create social geography. Some people might live closer to the protected core. Others might work in higher risk zones. Over generations, architecture can become class. What begins as radiation management can become political hierarchy unless deliberately prevented. Even the floor plan of a generation ship has ethics hidden inside it. The ship's relationship with Earth would also change with time. At first, Earth would be a living correspondent. Messages would arrive from people the crew knows. Mission control might advise, update, comfort, and celebrate. After a few decades, the delay to Earth would still be manageable for emotional messages, but useless for emergency help. After centuries, Earth becomes an archive that still speaks, but no longer belongs to the same historical moment. Its languages may have changed. Its politics may be unrecognizable. It may have lost interest in the mission, or become unable to communicate, or send faster probes that overtake the world ship. The crew may receive news that makes their own sacrifice seem obsolete. That possibility is sometimes called the incentive trap. If technology improves after launch, a later, faster mission may arrive first. For the shipborne society, this is not an abstract timing problem. It is an existential insult. Their entire culture might be built around a destination only to learn that someone else reached it generations earlier. This does not necessarily doom the mission, but it changes its meaning. The ship must be valuable as a world, even if it is overtaken. It must not be designed around being first, because firstness is fragile across centuries. It must be designed around carrying a viable branch of humanity, whether or not another branch arrives sooner by a better method. That is another reason the generation ship cannot be treated as merely a slow spacecraft. If a later breakthrough makes the original mission scientifically redundant, the people aboard remain morally non-redundant. Their lives cannot be dismissed as an outdated launch architecture. There is a technical echo of this in propulsion strategy. A ship launched at 1% of light speed may be overtaken by a probe launched 2 centuries later at 20% of light speed. The probe can deliver updated data, perhaps even instructions, but not necessarily material help. If the probe discovers that the target planet is unsuitable, the ship may not have enough delta V to redirect. If the probe discovers that the target is ideal, the ship still has centuries of aging left before arrival. A generation ship therefore needs a mission plan that can absorb new information arriving after launch, but not depend on information that may arrive too late. This is another form of latency, not between stars, but between knowledge and trajectory. Navigation itself is often simplified. The target star moves, the sun moves. The ship moves through a gravitational landscape influenced by stars, galactic tides, possible rogue planets, dark objects, and uncertainties in the target's long-term motion. Over a few decades, astrometry can be precise enough for robotic flybys. Over centuries, tiny uncertainties can accumulate. A crewed world ship would need autonomous navigation using onboard telescopes, inertial systems, pulsar timing perhaps, and constant recalculation. It must know not only where the target is, but where it will be when the ship arrives. The problem is solvable in principle, but it adds yet another system that must function across the entire voyage. A civilization can forget why a festival began and still survive. It cannot forget how to aim. Communication with the destination before arrival may be impossible if no infrastructure exists there. The ship can observe, but observations are limited by distance, instrument survival, and the changing geometry of approach. If it sends ahead fast scout probes, those probes require their own reliability and communication systems. If the scouts are launched late in the cruise, they may arrive only a little earlier than the main vessel. If launched early, they must survive even longer. Layering missions helps, but every layer is another reliability chain. Interstellar planning has this recursive quality. The solution to one uncertainty is another mission that inherits many of the same uncertainties in smaller form. The ship's economy would be unlike any economy on Earth. There is no growth in the ordinary sense because volume, mass, and energy are constrained. There is no external market. There is no import substitution because there are no imports. Wealth cannot simply be accumulated as possessions if storage, mass, and resource cycling are finite. The most valuable currency may be reliability, spare capacity, conserved materials, trained expertise, uncontaminated genetic lines, healthy soil cultures, low-stress social relations, and trust in institutions. Wastefulness is not merely immoral, it is physically dangerous. Yet a society built entirely around austerity may become brittle, joyless, and politically unstable. The ship would need an economy of sufficiency, not abundance, but it would still need celebration. That balance is not a minor cultural detail. It is survival engineering through social form. There would also be a problem of truth. In a closed mission, bad news can threaten social order. Leaders may be tempted to hide declining margins, radiation trends, genetic issues, or target uncertainty to prevent panic. But hiding reality makes adaptation harder. The crew must know enough to respond intelligently, yet not be overwhelmed into despair. Every society struggles with truth under pressure. On a generation ship, misinformation is not a media problem. It is atmospheric risk. If people stop trusting maintenance logs, food reports, medical advisories, or population plans, coordination fails. The ship must cultivate a culture where bad data is not punished, where admitting uncertainty is a civic duty, and where hope is not built on denial. That may be one of the hardest systems to engineer. The phrase mission success may need to be redefined. In a conventional space mission, success means reaching a target, collecting data, or delivering a payload. In a generation ship, success might mean that the people aboard remain healthy, free, knowledgeable, and capable, regardless of whether the original destination becomes viable. If the ship survives as a long-term habitat in interstellar space, is that failure? If it decides democratically to abandon arrival and remain a wandering civilization, is that betrayal? If its descendants choose to settle in the target system's asteroid belt instead of a planet, is the original dream broken or matured? The further a mission extends across generations, the less right the founders have to define its only acceptable ending. This is where the generation ship becomes almost philosophically dangerous. It forces us to ask whether exploration is about places or continuities. If the goal is simply to put human DNA under another star, a seed ship may be enough. If the goal is to preserve a culture, the culture will change. If the goal is to give descendants a better future, They may disagree about what better means. If the goal is species survival, the resources spent on one risky ship might instead build hundreds of resilient habitats inside the solar system. If the goal is knowledge, robotic probes are cheaper and less morally fraught. The generation ship is not automatically the rational answer to any one of these goals. It is a dramatic answer that must justify itself against alternatives. One alternative, often less glamorous but more powerful, is to expand through the solar system first and let time work for us rather than against us. Thousands of habitats around the sun, built from asteroid material, could create a distributed civilization with many ecological experiments, many governance models, and many technological lineages. Over centuries, such a civilization could learn which closed systems endure. It could test artificial gravity levels, multi-generation space medicine, long-term radiation shielding, and autonomous industry with the possibility of mutual aid. It could create the knowledge base that a generation ship would need. In that future, the ship to another star would not be a desperate ark. It would be a mature habitat choosing migration after proving that artificial worlds can remain alive. The ark metaphor is dangerous. It implies catastrophe behind and salvation ahead. It encourages urgency, secrecy, and moral shortcuts. A world ship built as an ark during civilizational panic might launch before its systems are ready, with governance shaped by fear and inequality. A world ship built as a migration vessel by a stable spacefaring civilization could launch with better testing, broader consent, and less mythic pressure. The same physical object could be either a lifeboat or a prison, depending on the society that builds it. Science can calculate shielding thickness and crop yields. It cannot redeem bad motives. The universe is not asking us to abandon the dream. It is asking us to mature it. A mature generation ship story would not begin with a countdown and cheering crowds. It would begin centuries earlier with small habitats failing safely near Earth. It would include legal arguments, ecological experiments, ugly design reviews, canceled prototypes, embarrassing failures, and generations of people learning how to live in artificial worlds without pretending those worlds are simple. It would treat the first successful closed habitat not as a stepping stone to escape Earth, but as a reason to understand Earth more deeply. After all, the only closed life support system known to support humans over geological time is the planet we are already on. There is a final scientific humility hidden in that comparison. Earth is not stable because it was designed. It is stable enough for us because life, geology, atmosphere, oceans, and sunlight have co-evolved across billions of years. It has endured mass extinctions, asteroid impacts, supervolcanoes, ice ages, oxygen revolutions, and continental rearrangements. Not because it is delicate, but because it is vast and self-buffering. A generation ship is delicate because it is small. It has no plate tectonics, no deep ocean, no atmospheric reservoir measured in quadrillions of tons, no wild biosphere with millions of species waiting to fill niches after disturbance. To build a ship that imitates a planet, we must first admit how little we understand about why planets work. Maybe that is the deepest value of the generation ship idea. It makes the ordinary miracles of planetary life visible. Fresh air becomes engineering. Soil becomes a technological marvel. Oceans become buffers. Weather becomes a distribution system. Biodiversity becomes insurance. Childhood becomes continuity. Culture becomes a life support loop. The fantasy of leaving Earth reveals how much Earth has been doing for free. If we ever cross to the stars, it will not be because we have outgrown planets. It will be because we have learned, painfully and precisely, how rare the services of a planet are. A practical mission plan would therefore have to carry an unusual kind of humility in its specifications. It would not write centuries of reliable operation as a requirement and move on. It would ask which century is expected to be hardest, which subsystems become most fragile after their original designers are dead, which social rituals protect technical competence, which supplies cannot be regenerated, which knowledge is tacit, which rights cannot be suspended in emergency, and which failures must be allowed to end the mission before they become worse than failure. That last point is grim, but necessary. A ship without an honorable abort condition can turn survival into cruelty. If the destination becomes impossible, if the ecosystem enters irreversible decline, if governance becomes abusive, the descendants need more than maintenance manuals. They need a moral language for choosing what kind of survival is still worth preserving. The public often asks whether humanity will one day become interstellar. A better question is whether humanity can become intergenerational in the strictest sense, capable of making promises that remain technically and ethically coherent when the promise makers are gone. We already struggle to maintain bridges, power grids, archives, treaties, forests, oceans, and climate commitments across decades. A generation ship extends the same problem until the metaphor becomes literal. Neglect the filters, and people suffocate. Neglect the school, and people forget how to repair the filters. Neglect justice, and people may refuse to repair them. The ship compresses civilization into a machine where every abstract virtue eventually becomes a physical variable. That is why the generation ship is less a prediction than a test. It asks whether intelligence can build not only engines, but continuity, not only habitats, but trustworthy futures, not only archives, but living memory. The stars may be reachable only by a society that has already learned the discipline the voyage demands before it leaves. The child in the sealed city grows older. The ship continues. Behind it, Earth has become a signal delayed by years, then decades, then perhaps only a memory preserved in archives. Ahead, a star brightens by an amount no eye can notice yet. Around the ship, dust strikes the shield one grain at a time. Inside, water moves through roots and filters. Teachers train apprentices. Engineers listen to pumps. Doctors watch genomes. Gardeners watch leaves. Laws are argued over. Stories change. Some systems fail and are repaired. Some are not. The mission survives if each generation receives enough order to pass on more order than it loses. That is the whole wager. Not that humanity can defeat entropy, but that for long enough, in one small moving world between stars, it can keep paying the price.